Okay, so let's do some calculations for experiment 4, kinetics. Kinetics. Okay. So for example, let's use e.g. Let's use A1 and B1. So A1 plus B1. Okay, we'll look at those two test tubes. Okay, so in A1, you placed in there 10.0 milliliters of potassium iodide. That was aqueous. You also placed in 5.0 milliliters of sodium thiosulfate, so Na2S2O3. That's again aqueous, so remember why you place this into there. And so that equals, the total volume is 15.0 milliliters. Okay? And in B1, you placed 10.0 milliliters of K2 S2O8. Again, that's aqueous. And you placed in 1 milliliter of starch. Okay? And so you know why you placed that into that test tube. So this is a total volume here of 11 milliliters. So overall, the total volume of the solution in which the reaction took place in, the total volume is the sum of those two volumes, A1 plus B1, which is equal to 26 milliliters, okay? Which again is equal to 0.026 liters, okay? So to find the concentration of I minus, okay, we just need to determine the number of moles of I minus and divide it by that 0.026 liters. So the concentration of I minus is equal to 0.01 liters of Ki multiplied by 0.1 mole, okay, per liter of Ki, which is equal to 0.001 mole of Ki. Now, if we divide that by 0.026 liters, that will then give us the molarity. Okay? And so the molarity is 0.0, let's see here, 3846. 3846. Okay? Now, likewise, the concentration of S2O8, 2 minus, okay? 2 minus. Again, in this case, for the B1 case, you had 0.01 liters of that multiplied by 0.1 mole per liter, okay, which is equal to 0.001 mole. And again, the volume is the same in this case. Notice that in the other trials it would be different. It is 0.026 liters, and we get the exact same value that we got up there, okay, for the concentration of S2O8 2 minus. Okay? So you vary these two concentrations to determine, well, we want to get the initial rate, but we also want to determine the rate law. So let's flip slides here, and locate my pen. Here we are. So the next part of what you want to do is you want to calculate what the initial rate is. So the initial rate, okay, of the reaction. Okay, and you can look in your lab manual and you'll find a lot of equations that will eventually lead to the equation that I put here. You want to look at all the assumptions leading to this equation to help you write your lab report. So this is 1/2 times the change in concentration of S2O3 2 minus, okay, divided by the change in time. Okay, so to find the concentration of S2O3 2 minus, similar procedure like we did in the previous. This is going to be equal to the volume that you added, so 0.005 liters, times the concentration, which you should have found on the bottle, is 0.005 moles per liter. Okay, we'll put it over here. So this equals 2.5 times 10 to the negative 5 moles. Okay, and again, the total volume was 26 milliliters. That's a liter, so that's 0.026 liters, which equals 9.615 in my case, times 10 to the negative 4 moles per liter. Okay, so I'm not going to worry about sig figs. You can think about that when you're writing your lab reports. So the change in concentration now of S2O3, okay, 2 minus, is just going to be equal to 9.615, okay, times 10 to the negative 4 minus 0. Okay, so it'll be this value here. Okay, so now to find divided by the change in time. Okay, so if we assume the change in time, let's say, is in my case, let's say I took 5.2 seconds on average of the 3 trials. So let's say delta t is equal to 5.2 seconds. Okay, so you just divide these two numbers. Therefore, we get 9.615 times 10 times 10 to the negative 4 moles per liter divided by 5.2 seconds, okay, and we get a value of 1.849 times 10 to the negative 4 moles per liter per second minus 1. Okay, and of course we have the 2 up here, so we have to divide by 2 to get the initial rate. So we divide by 2 to get the initial rate, and our value in this case turns out to be 9.245 times 10 to minus 5 moles per liter per second minus 1. Okay, so you're going to repeat the same type of calculation for A2 plus B2 and A3 plus B3. Okay, so moving on. So part of your objective is to determine the rate law once you have this data. So in terms of an equation for a rate law, the general form that you write is the rate is going to be equal to K, the rate constant, which is I minus. Okay. It's going to be raised to some power X times the concentration of S2O8, 2 minus raised to the power of Y. Okay. And so you can see your lecture notes as well. You can look in the textbook how you would calculate X and Y. Okay. Remember, you're going to have, say, a rate for one particular concentration of I minus, for example, and another particular concentration of I minus. Okay. And if I minus is kept constant in both cases, then you can then solve for how the rate is affected by the change in concentration of S2O8, and vice versa. If you change S2O8, if you keep S2O8 2 minus at the same concentration and then vary I minus, you can see how it varies in X. And you can calculate what X and Y is. So in this case, let's assume that I did the calculation and I got a rate law that is equal to K times I minus, okay, and let's say it's to the power of 2, okay, so it's second order times S2O8, 2 minus, okay, and to the power of 1, so it's first order. Okay. Let's assume that I got it. And I'm going to use this throughout. Okay. So the next thing you need to do is calculate K. Okay. So once you have the exponents, you know the concentrations, you know one of the rates, then you can solve for K. Okay, so you want to be able to calculate K, okay, for each of A1 plus B1, A2 plus B2, and also for A3 plus B3. Okay? And so, like I said, you know this concentration, you know this, you've calculated this, you know the rate, so the only unknown value you have to solve for is K. Okay, so just rearrange and calculate for K. So the other thing you need to do is you did this reaction at a series of different temperatures. So you want to also calculate K, the rate constant, for each of the 5 or more temperatures that you observed. 5 for each of the 5 temperatures. Okay? Each of the 5 temperatures. Okay? One thing you want to think is, how do you think temperature will affect K? Okay? So how will temperature affect K? Affect the rate constant. Okay? And second to the last thing you want to do is you also want to make a plot of the natural logarithm of K versus 1 over the temperature. Okay? And so from your textbook, you can get this equation, and also from your lab manual, the equation is ln K. Okay? This should give you a straight line is equal to ln, the natural log of A, minus the activation energy divided by the gas constant R, multiplied by 1 over T. Oops, 1 over T. Okay. And so this is an equation for a straight line. This is your Y equals, this will be your B, and this will be your M. Okay, so this will be your slope, okay, and this will be your X over here. So Y equals mx plus b. So your slope is equal to minus EA over R. Okay, so now you can calculate what activation energy is in your reaction, and your y-intercept, so the y-intercept, okay, that's going to be equal to the natural log of A. See if I have another room for a slide here. And so when you do the plot, so you're going to plot ln of K, and you're going to plot, ln of K, and we'll put an axis here, and we'll put 1 here, ln K as a function of 1 over T. You want to think for yourself, what is the slope, which way is the line going to slope? Is it going to be going in this direction? Okay. Or do you expect it to go in this direction? Okay, and you have that plot. Okay, and then the last thing you need to do for the lab is you have 4 mechanisms, I think, in the lab manual. 4 mechanisms, and you need to find out which one of those is consistent with the rate law that you determined. Okay, the rate law that you determined. Okay? And that's all you have to do. Okay, except write the lab report. That's the end of this video.